Hello everyone, we present our work on DIDER, Discovering Interpretable Dynamically Evolving Relations. This work was done at Honda Research Institute. In this work, we aim to estimate dynamic, interpretable and disentangled sequence of subinteractions from multi-agent observations without supervision. This is obtained by dividing the task of interaction prediction into subinteraction prediction at time t1 and duration estimation k. Here is the difference between per-step prediction of interactions versus disentangled interpretable prediction of interactions between two agents. In the figure on the left, per-step prediction of interactions results in noisy relations. On the other hand, the right figure represents the prediction of edge type and its corresponding duration of future time steps. Clearly, the right one is more interpretable. Our work DIDER presents an end-to-end interaction modeling framework which incorporates inherent interpretability. This is achieved by disentangling the sequence of interaction predictions into subinteraction prediction and duration estimation. We show that this disentangled representation improves performance on trajectory prediction tasks while also achieving better interpretability of interaction types. DIDER uses a conditional BI-like framework. The model takes input trajectory at time step t and outputs a future predicted trajectory. The latent embedding ZE represents the distribution of the edge types at time t, and ZD represents the distribution of time duration k for the predicted edge type. The decoder then uses the predicted edge type for future time duration k to predict the future trajectory of the agents. The model consists of two encoders shown here as duration encoder and edge encoder. During training, edge encoder computes the duration of edge types for every segment using information of the whole sequence of past and future trajectory. To model the true posterior over the latent space, we use reverse LSTM to capture the future states of sequence. We demonstrate the performance of DIDER on one synthetic and two naturalistic datasets. Synthetic dataset consists of three particles moving with dynamic interactions between them. Two particles move with constant velocity, while the third one is initialized with random velocity. The third particle is pushed away if the distance separating them is less than 1, and the type changes from interaction to no interaction. For the naturalistic dataset, we use basketball and indie dataset. Basketball dataset consists of trajectories of 5 players, and the model uses two interaction types, interaction and no interaction. Indie dataset is a naturalistic German intersections-based road user trajectory dataset. This dataset is suitable for a problem setting as it incorporates various temporal dynamic interactions between agents such as car following, yielding, passing by, cut-in, lane changing, etc. We use three baselines and ablation methods: Dynamic Neural Relational Inference, which predicts edge type at time step t, our proposed method DIDER with SCID, which is our framework, except that the duration encoder formulation is adopted from SCID framework. We use mean square error to evaluate the performance of the trajectory prediction task, and edge accuracy and dynamic edges visualization to measure the qualitative and quantitative analysis of interpretability. For the synthetic particles dataset, the results show that DIDER hours outperforms DNRI and DIDER with SCID in MSC as well as edge accuracy metrics. For the indie dataset, we do not have ground truth interactions, so we cannot directly measure the accuracy of each edge type in order to quantify the interpretability. Therefore, we conduct an ablation study with DIDER using various edge types from 2 to 8 and select the one with the least mean square error for the downstream trajectory prediction task. Based on MSC, we select 6 edge types. With 6 edge types, DIDER with SCID and DIDER hours outperforms DNRI for short horizon prediction, and DIDER hours outperforms other methods for long horizon prediction. Here are the visualizations of the temporal interactions between two agents, where one agent yields for the other at the intersection. The segmented temporal interactions show that DIDER is more interpretable as compared to DNRI, with per-step predictions of noisy interactions. For basketball dataset, the ground truth interaction types are not known, so evaluate only using MSC. The results show that DIDER with SCID and DIDER hours outperforms DNRI for short horizon prediction, and DIDER hours outperforms other methods for long horizon prediction. In conclusion, we introduced DIDER, an unsupervised framework that leverages disentangled sequence of sub-interactions to address interpretability in multi-agent interaction tasks. It targets a class of problems where interactions can be decomposed into a sequence of sub-interactions. It addresses this using two latent space representation without any supervision, and this is the first step towards development of inherently interpretable dynamic interaction models for multi-agent scenarios. One limitation of this work is that the learned disentangled interactions doesn't have any semantic meaning associated with them. This can be addressed by incorporating relational annotations of infrastructure and context representation to learn complex behaviors in traffic scenarios. Further, learning the causal graphs to provide human interpretable explanations of agent behavior and leveraging learned interpretable interactions to generate traverse trajectories could be the future work. With this, I conclude my presentation and thank you for your time and attention.